Can you hear me? Can you hear me? Okay, let's take it. Mm. I will. All right. Any questions? Anybody? Math, not math? No? Okay, good. Or maybe not good. I don't know. Okay, so yes, conjugate gradient. I hope I have enough material for today. Is it hard? Oh yeah, I have to do the convergence theorem. Okay, that will take time. Yes. So yeah, there's plenty of material. All right. Conjugate gradient, let me remind you the method. So um, it looks like gradient descent. So you have the next step getting shifted by some jump, and because it's hard to memorize, all I want you to be able to at least remember is that AK contains this factor QXK minus B, and like Mel answered last time, this guy goes to 0 because X star is equal to what? Q inverse B, right? And so, okay, so yeah, so it goes to 0. So that means AK goes to 0, okay? So you make smaller and smaller jumps, right? Which is what you want. You want to shrink your jump as you get closer. So if there's one way to memorize, just remember that, because that's really the heart. All right. Like meaning you know what the minimizer satisfies, you just don't want to invert because it costs a lot of RAM. Okay, if you work at Google, hopefully, or Microsoft, whatever you like, yes, Alpha 0. And then it converges in n steps. So that was the beautiful thing about this method. Okay, good. Let's do examples. All right. So the question is, minimize this quadratic and apply conjugate gradient. So what do? Step 1, find the eigenvectors. Okay, so these two are the eigenvectors for this 2 by 2 matrix. There's some formulas for eigenvectors, but yeah, you should memorize them because we will have a final exam and you can use Wolfram Alpha. So, you can cheat now. No, you don't cheat now, ever, but you won't be able to cheat, even if you want to. So maybe in the future we'll have iPads, but for now it's all paper. There was a nice formula I taught in 224. If you don't mind, I want to Google it. There was a formula for 2 by 2 eigenvector that I forgot, but I used it all the time. Yeah, so there was this like, I don't know if you can see it, but there was this formula down here, and these are the eigenvectors. Okay? Because I don't want you computing characteristic polynomials. Okay, so is that clear with everybody? So use the formula. Don't. And you know what? I might put it in the final, like the formula. No, you cannot, because people do like microtype and then use their glasses. No, I will give you this formula. I think I should, yeah. Let me remember this. So 2 by 2 eigenvector formula in sheet. What? Yeah, I'm saying to put in the final. I want to put this guy. Anyways, so you found the eigenvectors without using rule from alpha. And then these are the ones. And then let's apply the method. So step 1, you have an initial point and you use your formula. Should you memorize this formula? That's another good question. I ask my own questions. How are you going to memorize this? It's disgusting. I don't know. What do you think? Too much? Not your own, because this is bad. You might print the whole textbook. Okay, so I guess this formula should be. Huh? Beforehand on Quarkus, and then I will put it in the final. So you know what you don't have to memorize. Yeah. Anyhow, because I don't even remember this. So you have this, and then and G0 is complicated. Yeah, so I should give it absolutely. Yeah, so G0 is this difference. That's how I remember the method, that this should be going to 0. And yeah, you have to compute all this stuff. So so first, yeah, I computed so I should say what is what. So D0 is the 1, 0 vector. It's the first eigenvector. Okay. And underneath I have this quadratic form. And then this 1 minus 1 is this guy over here. Okay. So you do that, and that gives you x1. So what was x0? Oh, 0, 0. So the method went from 0, 0 to the first step at on the x-axis, right? So it's like, oh, that's terrible. Can't draw a line over here. Minus 1/4, 0, right? So it went like this from x0 to x1. Okay, any questions? No questions. No. So you do that. And now you have to find the second step, and hopefully you will remember that this will be the final step. Okay, because it's 2 by 2. So you do the same stuff. You evaluate Q of this guy minus B. And yeah, so this guy will be x2. And that's the final step. That will be the minimizer. Yeah, so now let me run the simulation, okay? So this is the matrix, okay? 4, 2, 2, minus 1, 1. And here, what was the minimizer? Yeah, so I'll run it again. So let me run it again. And so the first step, this guy, I don't know if you can see it, it's on the minus 140, and then you run it again, and you get the minimizer. And as you can see, who from MATLAB agrees, your minimizer is minus 1.5, which is what we got here. Okay, okay, good. That's it. That's the method. So expect a question like, I'll put some matrix form. Come on, like this guy, and then do gradient descent, do conjugate, and then if we have time, augment the Lagrangian, and you will have to compare them. Yeah, who goes faster and stuff like that. Yeah, that's a perfect question for the final, because you have plenty of time. Yes, to get tortured, to learn. Same thing. Yeah, so this is the method. They went from 0, 0 to -1/4, and then it went to the minimizer, -3/2. Okay, 2 steps at most. All right. Okay, so what do I want to talk about? Right, this is d0, this is dk plus 1. Sure. Wait, what do I want to talk about? Oh, yeah. Okay, good. Minimize. So what do I want to talk about? What am I talking about? Oh, yeah, okay, fine, whatever. So, as I said, you find the eigenvectors, but another way that we talked about it last time is you find the guy in the hyperspace. So let me go very quickly. Yeah, so we found that xk is a element of this hyperplane. So we have this crazy formula. But anyway, so and here's the formula if you want to use it. So yeah, D0 is this guy, and then if you want D1, let's do it step by step. This is too fast. So D1, so you want to be in the hyperplane. So let me write this carefully. So yeah, this is G1, and then this is B0, D0. So you have Q of this one, and then hopefully I won't screw this up. Then I use linearity like this, and then I have B. This would be okay, good. So this is anyways, the point is your next direction is picked by this hyperplane. Okay, so that's all I want to talk about. So this is the thing we talked about. about picking from hyperplane x0 plus b1, whatever. But I don't expect you to do this. The eigenvectors is a lot faster. So, but it's up to you, because eigenvectors is expensive. This is actually more concrete, because you each time you just have to compute qx of something. So this is for numerics. This is not for you. You understand? Okay, let me just say this is numerics. This is not theory, because eigenvectors are hard to compute. Too, eigenvectors take time. Anyways, whatever. Moving on. I just want to make this comment because I saw this online that numerically what people do is usually this. All right. And yeah, the iteration is the same. It's just forming these decays. Either you do eigenvectors, which I prefer, to be honest. It's more intuitive. Or you do this hyperplane method. Yeah, we talked about this and steps. And yeah, this is the thing we proved on Tuesday. And this was part of your exercise for this would be, so I put this in the homework. There's a bunch of questions to compute the rate of convergence, and they use this polynomial. It's not that hard, but we will, yeah, we won't have time today, but we might do it on Tuesday if people are lost. But you need this for the homework, so I just put it here. Right, so let's see how you apply it. You know, one problem with matrices is that they're not always diagonalizable, right? So you have multiplicity. So all that means here is that even though spaces are n, what if, you know, Q is not diagonalizable? Okay, diagonal. Let me say it differently. What if algebraic multiplicity? Okay, I don't know what you remember. You know, like they're not equal. Okay, so here the yeah, you have m eigenvalues, but they have multiplicity. So, you know, what if Q's eigenvalues? Let me say it that way. Have algebraic multiplicity bigger than 1. And that just meant when you factor your characteristic polynomial like that, you have this MKs, right? They're bigger than 1 here. All right, anyhow, whatever. Now, again, how do you find eigenvalues? If you remember, you had determinant of your matrix, and you know you had minus lambda, like A11, right? And minus lambda stuff, and you get the thing I wrote on the over here for K1 to M, where M is less than 1, n. And this is a polynomial, and it has zeros at the eigenvalues. Okay, so this is the polynomial they're talking about in the book. So it's just the characteristic polynomial. Okay, good. So this guy is the characteristic polynomial. Can someone tell me why is it 1? The top guy, do you remember? you forget all our 2 to 4. So the constant term is the determinant of Q. That's the, and yeah, it was the determinant of Q. Yeah, whatever. So they said the determinant of Q to be 1. Doesn't matter. So yeah, recall constant term is determinant of A. Okay, all right. So the theorem, which is in your main book, is the following, that is very similar. It's a different inequality instead of Kantorovich. It says that you can get the rate by taking the maximum of the characteristic. Okay, so if you like, in our language, this is just, the top guy. Like, so, okay, whatever, you'll do it in the homework. Anyway, so this is the rate. Oops. And then the comment we wanted to make here is that you can go faster. So if you have m eigenvalues, that means you have m eigenspaces. So then you have d0 to dm minus 1 directions. Okay. So you will go faster because you have fewer directions to move along. Okay. How else to say this? I mean, that's what it is. So that's the reason. So fewer directions, so it's much faster. So the worst case is when you have m equal n, because then you have to explore the entire space. All right. Okay, questions? All right. Maybe I can even do it now for you. I need to pick a matrix where the eigenvalues are the same. Let me take like something like this. Okay, so let's try it. Wow, blew up. What happened? Did I run something else? What do you want? It died. Okay, fine. I don't care. This will have gone in one step. So I'll try it next time. All right. Finally, let's do some theory. So we have, three algorithms. Two. Where is it? Three. Oh, no, we have three. Yeah, Newton's method, gradient descent, and conjugate gradient, conjugate direction. So now let's prove convergence for this stuff. Because I will do one more algorithm next week. So an algorithm is simply you take the previous step and map it to the next. Okay, so this is very general stuff. All right, so that's what they mean by algorithm in computer science. Okay, so you apply this function. And here are the assumptions. They're very general because we don't want to keep specifying. So first you need what is called contraction. Okay, so this is called contraction. Okay, so if you do a little bit of physics, you will see this under the name of fixed point. Okay, so whenever you have Yeah, exactly. So whenever you have decreasing, so you have some recursion, like AK plus 1, and you know is less than some sharp guy, AK, then you have that AK converges to some A star. This is called the fixed point. All right. So yeah, you need this. And so gamma is the solution set, right? What? Yeah, it's the same stuff. Yeah. So yeah, same stuff. And okay, what else will I talk about? Yeah, so you need contraction for your algorithm, otherwise you don't have convergence. If you're already in the stationary, so these are the solutions for the gradient. So gamma is basically all the v's, so that gradient of f of v is 0. Okay, all the stationary stuff. So if you're already in it, I don't care. I mean, you're in the solution space. But if you're outside, I need contraction so that I move away from it. Okay, so that's the intuition here. So suppose gamma is some sort of curve in space, and you start outside, you want to jump to it. Okay, but if you start inside, you want to stay in it. Okay, all right, good. What else? Yeah, you need continuity, so you don't want your algorithm to jump. Maybe you do, but not for this result. What else? Then the limit of any convergence subsequent solution. Yeah, okay. So here we're going to use compactness. So if you remember, let me say it again. So a compact set, omega, any xk sequence in omega has xkn going to x star. Okay, so the typical example is -1 to the n. So -1 to the n does not converge because it goes to 1 and -1. But x of 2n is always 1, so it goes to 1. Yeah, I know this is a stupid example. I can make it more complicated. Make it like 1 over n, right? And then x of, y of n, you have that y of 2n goes to 1. Good. So that's what we mean by subsequence. And this is unit compactness. So I don't know what field you will be, but everybody cares about limits, like central limit theorem, strong law, whatever you are. To get limits, you often need what's called compactness, so closed and bounded. Okay, so this is no different. We need this condition. Okay, all right. Yeah, okay, so let's explain what's going on. I should have put pause here. I don't know if this. What do I want to say? Yeah, I mean, I explained this. So we have this space gamma, and we have that A of xk sends you to the next step, xk plus 1. And then what you evaluated, so let me call it f just to not confuse you. So you have f of xk, and you want this to be bigger than A of xk. Okay, strictly bigger. So you want to have a minimization. Okay, so you have to start with x0, and if you start outside, you want to keep dropping down there, okay? And gamma is all the places where gradient of f is 0. Okay, I mean, this is an example, because anyways, yes. Oh my God, I didn't put any pause. Damn it. Okay, so I'll explain. All right, this is a mess. Okay, whatever, I'll do it here. All right, so yeah, this is very general theory. So I have some algorithm giving me the next steps. So I'm doing all three methods together. And I want to prove you that if it does converge to something, it converges to the stationary point, to the solution set. All right, let's do this slowly. So I know it's hard to visualize, so pretend D is our usual f of x, and take gamma in your head, even though this is general, to be the stationary points. Okay, now let's do this. So first, let me prove you that the function itself converges to this. So I'll do it on the side. So I'll prove the following. Suppose x of ki goes to x of star, then d of xki also goes to the limit. All right. Let's go. So first, we know that a of xki is equal to xki minus 1. So, yeah, whatever. And we also know that if you precompose by xki, then you're less than, if you start outside, less than the previous guy. Okay. All right. Yeah, okay. Step 2. By continuity, we have the following result. So let me talk about this. In general, this is a general result. Whenever you have that yn goes to y, you have that d of yn goes to dy. Okay, so let me talk about that a little bit. Why is that? So what is continuity? It says that for every epsilon, you can find delta so that x minus y less than delta implies d of x minus d of y less than epsilon. So now take y of n to be so close to y star that it's less than delta, okay? For all n bigger than some n epsilon. So then indeed you get d of yn minus d of y to be less than epsilon. And you can make a sequence out of it. So put an n here, take it like 1 over n, I don't care. All right. So this is called sequential continuity, and it gives you gives you this part. Okay. But then I had to minimize it, right? Yes. Yeah, okay, let's do it. Now, here's why this is annoying. We did this in analysis, but you haven't seen it. Whenever you have a subsequence, xki, going to some point x star, I will show you that you can show it for the full, called the mother sequence, okay? So this is not xki, this is xk. So this is called lifting subsequence to full sequence. I know this is but it's like you see it once and then you never have to know it again. All right. It's just like I have to prove because it's a general algorithm thing. Like I'm gonna use it next week. I wanna. All right. Okay. So from before we have that d of xki minus dx star is less than epsilon. Okay. That's because the subsequence converges. So we use this continuity I talked about in step 2. All right. Now, use that xki can be written as a of xk. So suppose, yeah, so when ki is bigger than k, okay? So let me put it here, ki minus k. Do you understand? At least this final step. This power just means composition. So all they're trying to tell you is x4 is equal to a composed with a, composed with a, composed with a of x0. Okay? So then we have that d of x4 is equal to d of a to the 4. Okay, x0. So then you can, what is it? You had this inequality, right? This was less than d of a3 x0, right? And less than d of a square x0 and so on. All right. So anyway, so the point is, since d of xki minus dx star is less than epsilon, so we want to bound this. We want this to be bigger than dxk. So to do this, I mean, I could ask you, but I'll do it. So I need to figure out, so xk needs to be written as a to some power of xki. Or what do I want? I want this to be some a, yeah, of xki, that's fine. So then, if you give me a subsequence element, I need to move a little bit ahead, okay? So take m to be k minus ki, and then you have the d of xki is bigger than d of a xki, which is bigger than d of m xki, which is equal to d of xk. All right. Okay. Probably everybody's lost. Okay, so why talk about this? Getting a subsequence to converge is very easy, all right? This result over here follows from math, okay? This is real analysis. If you do any computer science in life, you need to know if your algorithm converges. Like, that's how theoretical computer science make their bread, all right? Real analysis will tell you that if your set is compact, you have some subsequential limit. Now we're proving that in this contraction setting, when you have a contraction, d of ax less than d of x, then you can lift to the whole sequence. This is important because that means your algorithm will converge along every limit. Okay, you don't have to be very particular. And then that's important. For numerical methods, you don't want to force your computer to move along some sequence. You want to have the freedom to take any point along the sequence. Do you understand? Huh? A little bit? So that's why you need contraction in your algorithm, because you do not want to stay with the subsequence. You want to have the freedom to take any limit, right? To move along any way. Okay? And you can only guarantee that when you have contraction. If there's anything to remember, just remember this. That's all. That's all I want to talk about for here. Okay, and then let me finally prove to you that the minimizer falls into the solution set, which again, just think of it as the stationary points. Don't kill yourself over this. If you go higher up, you will see that there's other stuff. Okay. All right, let's do this. So we do it by contradiction. So suppose X star is not in the solution set, is not stationary. And right, so step one, if I blindly apply this algorithm to my fixed point, that's why it's called the fixed point, by the way, because when you apply your algorithm, you're supposed to come back to it. Okay, so this is what we're going to break. We know that what should happen is that A of X star should equal X star. That's why it's called fixed point. So whenever you hear this word, it just means that you have some algorithm, some operator, DEs, PDEs, where if you act on it, you get back the point itself. Okay? So we know we will use this. That's why we assume that you don't have this to get a contradiction. Okay, let's do it. So since X is not in gamma, you have a strict inequality. Okay, by assumption. If it was in it, it's bigger or equal. I want to prove it myself, but okay, let me do it. By continuity, we have the subsequence converging. So let me do it. Yeah, okay, I'll do it on the side. I'll do it with you. Okay, so again, we have a subsequence going to X star. We showed that, in fact, the whole sequence goes to the minimizer. That was step one. Step two, we want to show that the fixed point is inside the solution set. Think about it this way. Suppose not. If not, then by assumption, D of A of X star supposed to be less than D of X star. Okay, all right. But what is it? X of k converges to x star. Xki, yeah, xki goes to dx star, which means that d of xki goes to dx star. But the same is true if you take their functions. So, because the algorithm is supposed to be continuous. This also goes to x star. Okay, so this is called the triangle trick. You'll see it once. I probably forget it, but let me do it. So take the difference, d of ax star minus d of x star. Add and subtract the thing that they both are equal to. So minus d of x ki plus 1 plus d of ki plus 1 minus d of x ki plus d of x ki. I'll do it here. Why even kill myself over this? Okay. So I add and subtract these two guys, which I know the limit. All right. This guy is identically 0. So this is identically 0 because a of, oh, no, it's not identically 0. Sorry. So yeah, so the first guy goes to 0. Because composition of continuous is continuous. So since xki goes to x star, you have the composition of xki goes also to the x star. Okay, so that's why the first guy is 0, and the second guy we proved it above. So this was sequential continuity. Okay, and then so that proved, where is it? Upstairs. But here there is no ki. So you took the limit and it's itself, but the thing you bounded by is equal to 0. So that means this was always equal to 0. There is no ki there. Okay? And this is the contradiction, that in fact, this is a fixed point for your function. So you have, so indeed, d of ax star is a d of x star. All right. Anyways, all I want you to learn from this is that real analysis gives you this. You know there is a limit, but to have full convergence, you need contraction. At least remember that. I mean, so you always have some convergence by compactness, but to get the full thing, which is called fixed point theorems, you always need contraction. I mean, I don't care, economics, like in every theory, you will always come across some fixed point. So that's why Nash won his Nobel Prize. He proved, yeah. All right, what else? Right, so let me do the particular case. So in our particular case, we had a of x was equal to, let me do the discrete. A of xk was equal to xk minus ak, gradient of f of xk, right? This was called gradient descent. And I don't know if you remember, but the way we picked this was so that it's the minimum jump, right? Is that okay? So that's why you get this inequality. So indeed, it's a contraction. All right, so the gradient descent falls into the global convergence theorem. Okay. So, okay, anyhow, whatever. The point is, if you come across an algorithm and you don't know if it converges, you can use this general result. Okay, because you will come across algorithms in your life. So just know that there are results out there to prove convergence. Okay? Well, I don't know, that's all. All right, thank you. Yeah,